All right, let's get right into it. We're surrounded by machines, right? In our factories, our power plants, everywhere. But how do we know if they're healthy or if they're about to have a really, really bad day? Well, the answer, believe it or not, is hidden in their vibrations.
Just think about that for a second. What if a huge critical piece of machinery could just raise its hand and say, hey, I'm not feeling so good. I think I'm going to need some attention in about 2 weeks. This isn't some far-off sci-fi idea. It's the whole point of predictive maintenance, and it all starts with learning how to listen. You see, machines are talking to us all the time. They're communicating through the language of vibration. The trick is figuring out how to translate that language into something we can actually use, something that tells us what's really going on inside. Think of it kind of like a heartbeat. A healthy machine has this steady, predictable rhythm, its own unique signature. But the moment a problem starts to brew, even a tiny crack in a bearing or a gear that's just a little bit off, that signature starts to change. And those changes, they're the first whispers that trouble is on the way. So this is where the science comes in. The formal name for it is vibration analysis, and it's all about measuring these tiny movements to spot those telltale problems. We attach these little sensors to the machine, and they capture all that vibrational data so we can start decoding it. Okay, so we've got this raw, kind of chaotic vibration signal. How in the world do we turn that jumbled mess into a clear diagnosis? How do we translate the machine's language into something a person can actually look at and understand?
Well, it boils down to 3 main steps. First, that sensor, it's called an accelerometer, it captures the signal. But like I said, it's super complex. So for step 2, we use this amazing mathematical tool called the fast Fourier transform, or FFT. What the FFT does is basically acts like a prism. It takes that complex signal and breaks it down into all of its individual frequencies. And suddenly, step 3, you have a clear frequency chart where specific problems actually show up as visible specs.
And trust me, that is not an exaggeration. The FFT is the absolute cornerstone of this whole field. It's the magic trick that turns all that noise into clean, usable data, letting us literally see what's going on inside a machine. But this also creates a brand new problem. Because while the FFT gives us the data, imagine trying to stare at thousands of these charts from hundreds of different machines all day, every day. It's just an impossible amount of information for a human to process. And that is where we bring in the real expert. Artificial intelligence. AI can do what we simply can't. It can just tirelessly swim through these massive oceans of vibration data 24/7 and spot these subtle developing patterns that would be completely invisible to you and me. And for this very specific job, there are 2 AI specialists that we really rely on. So let's meet them. In one corner, we have convolutional neural networks. We just call them CNNs. And in the other corner, we have long short-term memory networks, or LSTMs. Now, they both analyze vibrations, but they do it in ways that are fundamentally different. I love this way of thinking about it. The CNN is like a spatial pattern detective. It's absolutely brilliant at looking at a single snapshot of the vibration data and finding a specific clue, a specific fault signature. The LSTM, though, is the temporal trend forecaster. It's not just looking at one moment in time, it's analyzing the entire story of how the vibration changes to predict what's going to happen down the road. Now, the really clever trick with the CNN is how it sees the data. It takes that 1D vibration signal, which is basically just a squiggly line, and it converts it into a 2D image, something called a spectrogram. This turns the problem from signal analysis into image recognition, which is something CNNs are just world-class at.
And their performance? It is absolutely staggering. CNNs can hit over 99% accuracy in classifying faults. Think about that. That means it can look at that vibration image and tell you with insane precision, not just that a bearing is failing, but whether the damage is on the inner ring versus the outer ring. That's the power of the pattern detective.
LSTMs, on the other hand, come at it from a totally different angle. They don't need to turn the data into a picture. They work directly with the raw 1D time series data. Their whole structure is built to understand sequences, to see how one event leads to the next, and to spot the bigger trend as it unfolds over time. And that's exactly where the LSTM really shines. Its whole game is prediction. Its main job is to forecast what's called the remaining useful life, or RUL, of a part. By analyzing that long-term trend of how things are slowly getting worse, an LSTM can answer the most important question of all, not if the machine will fail, but when. Okay, if you remember one thing, make it this analogy. A CNN is like taking a super high-resolution photograph of the vibration at one specific moment to tell you exactly what's wrong right now. An LSTM, though, is like watching the entire video of the machine's life, seeing how the vibrations slowly change over weeks or months to predict how the story ends.
So let's just break that down one more time. CNNs are all about spatial patterns in 2D images, and their goal is super accurate fault classification. LSTMs are about temporal relationships in 1D data, and their goal is trend prediction. One tells you what is broken, and the other tells you when it will break. Two different experts for two different but equally crucial jobs.
But what if you need both? I mean, in the real world, you want to know what's wrong, and you want to know when it's going to become a major problem. Well, the cool thing about modern AI is you don't actually have to choose. The cutting-edge approach now is to build hybrid models that actually combine the strengths of both. In these systems, the CNN goes first. It acts as the feature extractor, looking at that vibration photo and picking out the most important patterns. Then, the LSTM takes that stream of important features and analyzes how they change over time. It's like having the detective find the clues and the forecaster watch a video of only those clues. You get the ultimate diagnostic.
So, where is all this going? What does it really mean when our machines can talk to us and we have these incredibly smart AI translators that understand every single detail of what they're saying? So, let's boil it all down. The biggest thing here is that AI lets us shift from being reactive, fixing things after they break, to being truly proactive. It gives us insights that are so much deeper than we've ever had before, with specialized tools like CNNs for identifying problems and LSTMs for predicting them. And by combining them, we get the absolute best of both worlds. At the end of the day, this tech is helping us build a world that is smarter, safer, and just way more efficient.
This whole revolution in listening to machines is really just the beginning. We've taught an AI to understand the incredibly subtle language of vibrations. It really makes you wonder, doesn't it? As AI gets better and better at mastering these hidden languages all around us, what other invisible worlds, what other secret patterns is it going to reveal to us next?